I'm a CTO at FMI Technologies and research affiliate at IAS. And FMI is a firm run by physicists that seeks to use physics-inspired tools and methods to essentially forecast financial time series, if you may call it. So we have a couple of hedge funds now, and what we do concerns high algorithmic trading at medium to high frequencies. So that's somewhat the background I have. Today I'll talk not so much about trading and explicitly financial time series, but I'll focus more on a certain area of quantitative finance, which has to do with options pricing, and also certain approaches to it that involve using physics-based methods to characterize the dynamics of options prices. And the techniques are general. They can be applied beyond options as well to a variety of stochastic processes. This is actually part two of a talk I gave at this conference in January, where I spoke in detail about symmetries and symmetric groups. So I think I'll kind of skim over that, and I'll get to the point about the black holes, I think, hopefully sooner. So, there's been a bunch of work done in this field of econophysics. People have used path integrals to model options and equity dynamics. They've used theories, related to phase transitions, turbulence, and even recently gravity duals. And you don't need to know what all these things mean. All you need to know is that one feature crucial to all these physics-based approaches is the use of symmetries or symmetry groups to constrain the dynamics of these systems. So, I'll just explain what it is and motivate that, and then I'll skim over the use of symmetries. So essentially, a symmetric group is a set of all possible transformations that leave a system unchanged. So in this case, it's just different kinds of rotations, and then rotations are 120, and then and also reflections. But it was in 1978. So groups have been known for a long time, but it was only in 1978 that Sasha Polyakov had a dream to characterize the dynamics of systems that would otherwise be described by path integrals or SDs solely in terms of symmetric groups. And he launched this so-called conformal bootstrap program, which in finance terms is numerai invariant, and unlike SDs, also describes multi-scale dynamics. And in financial time series, like symmetries have been known for a while. So, time translation and log price translation invariance are assumptions that most modelers make. And self-similarity of time series has been known since the time of Mandelbrot, who noticed it for cotton prices. So the fact that you can zoom in and zoom out of these price processes without changing the statistical properties of these processes. And these symmetries appear to hold in actual markets. And also in crash modeling, where people such as Johansson have used multi-agent models to essentially characterize crashes, even in these, they have found certain modified versions of these scaling symmetries, such as the fact that the deviation of price from the critical price at the time of a crash is also described by these power law scalings with these complex critical exponents. And anyway, the point is that there are lots of motivations, and the final one, which is maybe the most useful to us today, is the fact that since 1998, in quantum theory, that the different dynamics of nonlinear or strongly coupled quantum systems has been described by linearized, so-called gravitational systems in one higher dimensional, where gravitational is a purely mathematical term here that means, in a sense, geometric, and you can essentially map observables from the bulk to the boundary, and do the simpler calculation in the bulk, and get the more complicated results on the boundary. And Yu Nakayama had constructed holographic duals for markets, for financial markets, using Lifshitz invariance. So, that's one of the things I plan to use. And So yeah, uh, I mean, so what I would do in the first version of this talk is basically introduce Lie groups and run through the general program. So I'll just explain the philosophy of what I do without going into the details of the calculations. What I would do is that we start with the symmetry group G and write down its Lie algebra, and then write down what that Lie group is doing to log price times space. And I would impose that these observables are invariant under the action of these representations, and then see what leverage we can get by just using symmetry groups without without looking at PDs and SDs in the first place. And what I would constrain are different observables of these price processes, which can be expectation values. They can be 2-point density functions, higher point density functions, or autocorrelation functions, etc. But the only one most people are concerned with are the two-point density functions, which are used in options pricing. And essentially, I'll just skim over this. It's not important for you to know what these symbols mean. All that's important is that all these symbols essentially, like characterize the generators of this Lie group, and these are basically commutation relations, which tell you how they fail to commute with each other. And just using this, we can get tremendous leverage. So after doing this, we write down representations of these symbols. So what these symbols are doing to price and time, or to space and time, if you're if you so like to think of things that way. So H is just shifting time back and forth. P is just shifting price back and forth. G is basically kind of rotating the price and time axes with respect to each other, and expansions and dilatations are C and D are kind of zooming in and zooming out of your price process. And we want that all our observables are invariant under the actions of the generators. So we start with applying them one by one. So for the 1-point function, it's trivial, you just get a constant. But for the 2-point density function, for instance, you apply log price and time transition invariance to get the fact that your density function does not depend on price and time independently, but it depends only on the difference between them. And you impose scale invariance to get your 2-point function to be of this form. You determine it up to an arbitrary function of this cross ratio, and you impose boosts, and you get that this arbitrary function has to be an exponential, and you transform back to canonical coordinates, and you get essentially a nonlinear generalization of Black-Scholes. So it's almost Black-Scholes, but it's allowed to be nonlinear because this delta in the denominator is allowed to differ from half, which would be its Black-Scholes value. And if you were to assume like a PD, you would see that the extent to which your delta deviates from half can be expressed as a power series in the nonlinearity by which you deform the Black-Scholes equation. So this is pretty cool that even just by using symmetry groups, you discovered nonlinear dynamics that of a kind that you perhaps would have been much more difficult by using PDs or SDs. And so essentially I play a similar kind of game for crashes, where it's observed that time and price scale with the same factor here, and not off by a factor of 2. So your Hurst exponent now goes to 1, whereas it was half in the case of Black-Scholes. And you get another point of enhanced symmetry, the 2D conformal group. And this also corresponds to going to a kind of, in a rough sense, going to an infinite volume limit of infinite volatility limit of Black-Scholes. So I would, I play the same game here. Again, you don't need to go into the details of these calculations, but the point is that by assuming invariance under the generators of your 2D conformal group, you again, get a 2-point density function, which is completely determined up to constant factor. And by going back to canonical coordinates, you get essentially two-point function, which is a Cauchy two-point function, which people have empirically observed. You see in terms of financial crashes, such as the COVID-induced crash in March 2020. Um, so you can again play the PDE game and try to relate these to PDEs, and you find that so if you try to write down PDEs essentially corresponding to Black-Scholes and nonlinear generalizations, you find that essentially if you try to set mass to zero in for instance this deformed version of Black-Scholes, you get a different group than if it tends to zero. So it's order of limits issue, and financially, like that's the difference between setting volatility to infinity or making it tend to infinity. And you'll see that essentially so if you set volatility to infinity, you will get another group, which is the M conformal group, and we'll see later how you can get it through other techniques as well, using holographic embedding. So I mean, the point is just to give you a flavor of what different groups can do and the power that they have. The most general kind of scaling is where time and price scale differently, but now time scales by if you set time to lambda to the z times time and price to lambda times log price to lambda times log price, you get an invariance where z is arbitrary, and you see that okay, z equals 2 will describe Black-Scholes, or z equals 1 describes the conformal markets which correspond to crashes. But maybe the most realistic model, or to describe data at least in equity markets, is when z is like dynamical and it changes rapidly, and or at least when z is fixed, we know we get the like Lifshitz group, which we can talk about, and then we can think about the dynamics right at the end when we talk about black holes and such things. So the Lifshitz group is really simple. It just consists of three operators, the time translation, log price translation, and the dilatations. You're just shifting time and price and scaling, and you get that just imposing invariance under this constrains your two-point function again up to an arbitrary function of this particular cross ratio, which is kind of related to distance to default and credit modeling. But in this context, it's just a cross ratio, and the Lifshitz group is not constraining enough to give you something more than that. There's a boost enhanced Lifshitz group. You can play the same game, and essentially what ends up happening is that, and then you can end up making a connection to a PD. It turns out that many people are familiar with fractional Brownian motions, where you have these fractional powers of these different derivatives, spatial and temporal derivatives, and it turns out that these Lifshitz symmetries are related, or they're related to generalized fractional Brownian motions as well, and you can play like different games describing the dynamics of these FBMs using Lifshitz symmetry. And the basic summary of this whole group theoretic description is that you have we've seen the interplay between four groups. You have the nonlinear Black-Scholes equation described by the Schrodinger group, and if you go to the large volatility limit, but you do not set it to infinity, you get the massive conformal group. And if you set it to infinite volatility, you get exactly the nonlinear conformal group, the 2D conformal group. And if you play the game from the other side, that there's another way to approach this crash dynamics, and like that is through the Lifshitz group, where you can dynamically vary your z from from 2 to 1, or your Hurst exponent from half to 1, and again approach crash dynamics. Now, this is kind of a recap of my previous talk. The main focus of this talk is this whole notion of holography, which was championed in quantum theory by Juan Maldacena in 1998, where he discovered that strongly coupled conformal theories in or strongly coupled, which means like nonlinear, which are essentially nonlinear stochastic processes under stochastic quantization. So these highly nonlinear processes, when you embed them in one higher dimension, they become linearized, and things look much more beautiful. Like that's what we can do in a variety of different ways. First, I'll give you like a toy model of how this can happen in a very controlled case, and then I think we'll get into holography proper, which is more complicated. So here, so you start with this Klein-Gordon equation in 3 dimensions, which is invariant under the 3D conformal group. So you just have a free equation. There is no nonlinear term, no nonlinear deformation. And if you introduce light cone coordinates, you can actually write it this way, where you can express it in terms of the light cone coordinates. And you see that if you fix this partial derivative with respect to one of the light cone coordinates, if you fix it to some m, so that's equivalent to making this following ansatz, you will get a familiar kind of equation with the one time derivative and like a double price or spatial derivative. And this is essentially under a change of coordinates, and making mass or sending this m to making it under analytical continuation. This is the same as the Schrodinger equation or your Black-Scholes equation, right? So you've essentially introduced, by dimensionally reducing from 3 dimensions to 2 dimensions, you've introduced a particular mass scale in the problem, or like a time scale or a length scale in your problem. And the same thing like can also be done. So what's the use of doing that? The use of doing that is that say 2-point functions are much easier to calculate in the 3-dimensional theory than in the like 2-dimensional one. And so you do the calculation in 3D. It's really simple. They are conformal 2-point functions, and you apply this partial Fourier transform. You do this light cone reduction from d+1 to d dimensions, and by doing that, you remove the fractional derivative out, and then you solve this integral to actually get the Black-Scholes or the Schrodinger equation 2-point function, or the Black-Scholes density function, from an object that was much simpler, which belonged to a much simpler group. So, and you can play the same game by, again, starting with the same Klein-Gordon equation in three dimensions, but instead of fixing the derivative along the light cone coordinate, if you just fix it along a spatial coordinate, you will get this familiar equation, which is kind of like a massive Klein-Gordon equation. And you get that you can change between the phi variable in 3 dimensions and the psi variable in 2D, again using another kind of partial Fourier transform, if you may say so. And you get that all expectation values of interest in your, for instance, Black-Scholes or your massive conformal theory, they can be obtained from this null reduction of the same observable in your high dimensional theory by applying these suitable transforms. And so in the M conformal case, you play the same game, and you get these k like Bessel functions, which were found by Kakushadze as well, and they reduce to Black-Scholes at small volatility, and this is essentially the same as like a large volatility limit that interpolates between Black-Scholes dynamics at one end and conformal dynamics at the other end. And so why do these techniques work at all? It seems like there should be no reason that they should work. It seems kind of like an accident, but it's not. It's completely obvious from the point of view of group theory. The fact is that if you didn't look at dynamics at all, at what's happening to price and time, but you just looked at those weird symbols, right, which had those commutation relations. If you just looked at all the generators of these groups, you would find that you would get, you can, for instance, start with the higher dimensional group, like a conformal group, and you can get the lower dimensional group by actually fixing certain generators, to constants, which is akin to taking the centralizer of the group, if you know what that means. So, by playing this game, you will actually get another group that lives in a lower dimension, which will be, in the case of, say, a null reduction, it will be the Schrodinger group, and in case of a spatial reduction, or by fixing the derivative along a spatial direction, it will be the M conformal group. So it's not an accident. It's a implication of group theory, So, but if you notice, we've mostly been working with kind of linear theories. None of these have had fancy nonlinear terms that would make them hard to solve in the first place. So, maybe you would say that, okay, what's the use of embedding in higher dimensions? The thing is, there is a much more general result, which is much less established. There's a lot of research going on in physics in this field, and a lot of people are trying to understand it and prove it. But this relates actually nonlinear theories now in d dimensions to the linearized versions in like d+1 dimensions. And now those linearized versions in d+1 dimensions are so-called gravitational theories, which have these diffeomorphism and invariance, and it essentially you can think of them as living on geometric surfaces or manifolds. So they're described by something called a metric, which kind of tells you how easy or hard it is essentially to go in different directions, or like how one time step in one direction in your coordinate space that translates to the motion in your canonical coordinates. And so the only coordinate invariant observable under symmetry assumptions is the curvature, which is also is a rank 4 tensor. And roughly, if you don't know any of this, that doesn't matter. You can think of the curvature of the manifold as just the extent to which the angles or the triangles drawn on the surfaces, the extent to which the sums of their angles deviate from 180. If they're less than 180, that's negatively curved. If there's more than 180, it's positively curved. And there are three spaces that have basically constant curvature, which live in a 4-dimensional space-time. So it's Minkowski, which is flat space, it's ADS, negatively curved, and DS, which is positively curved. And the one that we'll be interested in is ADS space, because that's the one where you see the linearized theories live, essentially. These gravity duals live. And so the gravity dual is not just a vague analogy between your boundary theory and your bulk theory. It's a very precise statement, and expectation values of your boundary can be actually got from expectation values of the bulk by fixing your radial direction to 0. And even the 2-point functions, the 2-point density functions match in this way. That they can be gotten from this kind of this kind of reduction to z equals 0. So it's not a fancy Fourier transform, partial Fourier transform like before, but now it's actually something much simpler, where you just take the pullback of that observable to that lower dimensional boundary, and you get what you want. So before going into the more complicated cases, you can ask what is the gravity dual to like just regular Black-Scholes or different kinds of Brownian motions, fractional Brownian motions. And it turns out that for a general Brownian motion with no nonlinear terms, this metric describes the dual theory, the gravity dual, and you can actually check that the symmetry of this like metric is, if you actually reduce that to the surface z equals 0, it's the same as the scaling symmetry of Black-Scholes for z equals 2, or crash dynamics for z equals 1, or for Lifshitz dynamic for arbitrary z. So that's easy to check, but what's highly non-trivial is that the dynamics in the bulk and the boundary will also match. And in this case, your log price expectation is just dual to free field theory. Both theories have kind of trivial dynamics, so we can we can kind of so it's a trivial case. So where the story gets much more interesting is when your boundary theory is kind of like nonlinear. So for instance, if you have this kind of equation with fractional derivatives and arbitrary potential in the bulk, like that will be dual to this kind of equation, which looks like a free theory on a curved surface, and the curved surface is your Lifshitz background, and you can plug in the actual metrics to get an exact expression for these kinds of like variables. You can solve this equation in for instance Fourier space. You can solve it to get something in terms of gamma functions. And the most remarkable thing I want you to take away from this is that the boundary equation is highly nonlinear and has fractional derivatives, and would be otherwise very painful to solve. Probably pages of calculation. But in the bulk, it's essentially a kind of a linear theory. It's just some differential operator acting on your wave function or your expectation value of your price, for instance. And all the nonlinearity is kind of encoded in this like mass term and these powers of R. Essentially, there's no hidden nonlinearity here. So yeah, I mean, this was in the case where initial conditions are well known, and you have these free fields in the bulk. So what's a more interesting case is when you would have black hole physics in the bulk, and that would essentially correspond to having probabilistic initial conditions for your theory on the boundary. So before getting into that, what is a black hole? It's just a solution to Einstein's equations, which like describes highly compact massive objects where light cannot escape. And as Einstein said, black holes are where God divides by zero. So you have essentially, roughly speaking, you have space going this way, and then you have like time going this way, and you have when you have a mass that's compact enough, there'll be a point where your spatial part of your metric turns into time, and then time turns into space. And so if you go inside a black hole, going forward in space is as inevitable as, say, going forward in time for us. And you go ahead and you hit the singularity, which is actually a point. But these coordinates don't make that evident. But that's essentially what a black hole is. And in terms of the metric, we spoke about metrics. So in terms of a metric, it can be described by like this particular form. And you see that where R goes to 2gm, there's this seems to blow up, seems to be in kind of infinity there, and R equals 0, there seems to be an infinity there. The first one is just a coordinate artifact. The second one is an actual singularity, which is at the center of the black hole, where radius goes to 0, your curvature goes to infinity, and the other one is just like donates a value of R beyond which you can never come back. So there's this whole literature on this. It's a big topic. So we're not going to talk much about go into much of the details, except that as most of you probably know, the Nobel Prize in Physics in 2020 was also awarded to Roger Penrose for the discovery that black holes are a robust prediction of general relativity. Now, if there's one takeaway from my talk, it's that there are robust descriptions of stochastic dynamics with these thermal properties as well. And what are these thermal properties? There are forward starting options have these thermal properties because their initial statistics are not fixed, but they're averaged over a bunch of initial conditions. And also, what's fascinating is that crash dynamics can be fully described by this black hole in the bulk as well. So far we don't have a good model for the onset of a crash and the end of the crash. Usually people have piecewise models for different parts of it, but my claim is that by adding these shocks to your price process, which are essentially quenched SDs, and studying the dual of this quenching, which is akin to black hole formation in the bulk, you can get a fully analytical model of essentially crash of financial crashes. And again, equations simplify in the bulk. They're easy to solve. What you end up describing is a crash is basically on the boundary is a gravitational shell actually collapsing to the bulk, and you'll see that you get observables that match, and also that you get something very intuitive, which is that information transfer from large scales to small scales happens, which is what you expect in a financial crash as well. And not only does this math describe the onset of a crash, but it also describes the end of a crash. The fact that, and that's akin to the black hole essentially evaporating through Hawking radiation, and it evaporates using this formula in like certain limits you get from the earlier equation, and you get that your time to evaporate, or which is the time for the crash to end or to subside, is obviously much longer than the time for the onset of the crash. So this is a qualitative way where you have this black hole physics in the bulk that qualitatively reproduces what you expect on the boundary, which is that crashes happen rapidly and then subside slowly, and also that the flow of information goes from long to short time scales. There are other applications of this that you can just briefly look at. This bulk theories help you look at dynamical fractals, which are much harder to do using just the boundary SDs. You can try to reproduce volatility smiles or skews using RG or based methods, which are roughly, the RG parameter is the radial parameter in the holographic description. And you can have different kinds of C theorems which give you results that SDs will not, which is that if you have 2-point density functions with these C values, and you change the scale at which these are being calibrated, these C functions will tell you that these C's will actually decrease with the scale. And the whole again, these are much more easy to see using the bulk theory than the boundary. And I think I'm done now, and I'm over time. This is a huge topic, and please actually reach out to me if you have further questions, and if you would